Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Kirk Gray.
And this is Fred Schenkelberg. Hey, Kirk. Good talking to you again.
Yeah, Fred, good to hear from you.
Hey, I got a question, and it spun off a thought that I think we could talk about today, if you're open for that. And one of our listeners, actually in the last week or so, I've gotten about 5 or 6 different questions, but this one was particularly interesting. Is they were focusing in, and I'm going to, paraphrase here, but they were focusing on crack propagation on this different types of equipment. And he was interested in, or they were interested, I don't know what their pronouns are, I've done time to failure data analysis in my previous work, but I don't think that we don't have failures. We have cracks that are growing and we want to know how long they'll last. And I thought, well, that's degradation analysis. And it's a little bit different. And there's ways to go about it. And I says, well, what else are you worried about with these products? Because crack propagation is one failure. Right. And then there was a quick discussion back and forth about that. Well, that's what he's been asked to work on. It was just this part of it. And I said, okay, well, right. That's fair. But I know that you've run into this where you get a team that's, I'm only going to do solder joints. And then you find out that they buy really crap components that don't really work even when they're properly soldered on a board. Right.
Or, have a delamination packaging issue or,
Yeah.
something like that. Right.
And I think you were mentioning when we were just chatting here for a minute, you said, just the circuit board itself has so many ways it can fail.
Oh, yeah. And so many manufacturing variations that affect those.
Yeah.
And that's the problem. It's isolating. Okay. When we test something, we're really limited on how many factors we can test at one time and be able to attribute the rate or change in rate of, say, crack propagation in our calculations or our measurements. And, you can do design of experiments and try and model that. But the reality is also you're only modeling probably an ideal manufactured condition.
Yeah.
And that's another problem.
Well, I'm thinking of this crack situation is that, if you're looking at it just from thermal cycling, right? And that's common. We'll do thermal cycling and use that to do cracks. But if you're an aircraft and you're looking at cracks in that on the fuselage, it's pressurization and depressurization, putting this pressure on it. And so you could do that. But in reality, it's those cracks will propagate with every time you land. There's a shock to the whole system.
Right.
That's different than compression. And then there's freeze thaw, and it's freeze thaw with a little bit of moisture in it, that makes the cracks go. It takes apart granite. I'm quite sure it'll take apart steel. And then you get this exposed metals that then start to corrode. And then somebody sticks their chewing gum in it, and so it gets this biohazard in there. It's just,
And then the duct tape on top of that.
That's right. And baling wire, but it's one of those things where we isolate, a single stress in a single mechanism because our experimental minds can wrap around when we simplify it to a larger degree. And now one of the arguments is that the dominant stress is like on an aircraft fuselage is the compression cycles.
Right. The expansion contraction is a pressurized at altitude. And, it's just, there's temperature gradients across that a whole system.
Well, there's load, where it's attached, and the wings put a bunch of weight on it in different ways than the nose cone does.
From the engines.
And from air turbulence and from people walking on it. And
I would imagine that, you do have some feedback or some recording of these. You can easily do that on many aircraft, and do kind of a summary or condensed, profile of some of those stresses from, you have to do an average of a lot of planes,
Yeah.
or whatever the structure is, like a 737, Boeing 737, the wings,
Yeah.
Boeing does do fatigue load testing, and they do, at least the engineers that showed me this show that they actually fatigue to a point of failure in the factory on maybe one, probably they can't afford a whole lot of them,
Well,
but they
yeah.
do that to an actual wing. They'll
But it's
load it
compared
till it
to,
breaks.
and it's compared to their modeling
Right.
and simulation work
Right.
and stuff. And they use that not to do the data analysis, but to confirm their modeling.
Exactly.
Right. Now, Seinberg, and I'm drawing a blank on his first name. I believe it was John, but I'm not sure. He's written a number of books on vibration and vibration analysis, and the degradation vibration contributes. And he did a lot of work in the aircraft industry.
Right.
And one of the takeaways from that is that, and I also ran into this with somebody who was looking at tracking how much vibration and shock packages got. They were shipping something through the system, and they would put accelerometers in there and measure it. And it was explained to me by both these folks that, if I get 2 or 3 2-foot drops, off of a conveyor belt or off of a truck, all the other vibration is inconsequential.
Right. Because the reality is that the shock and vibration from, road truck hauling and even loading and unloading is fairly mild, 1 to 2 Gs, as I understand it.
Right. But you hit a big pothole or you get in an accident, now you got a 50 G event, and all the other stuff doesn't matter.
Right. The shocks, a very high pulse shock essentially rings the product in all of its frequencies, and causes the most extensive fatigue damage. That's why repetitive, those pneumatic, what we call halt vibration, pneumatic repetitive shock systems are the most fatigue damage, creating.
Well, because they hit so many frequencies simultaneously.
Right. They're single point shocks. And as we know from Fourier transforms, or the math,
the fun math stuff
that I never used, that an ideal pulse, an ideal time zero has equal frequencies, is a summation of all frequencies, and essentially that's what you're doing when you hit an object with a hammer. You're stimulating all its natural resonances, and that's where fatigue damage occurs. If it doesn't resonate in its natural resonance frequencies, then you're not creating fatigue damage. If it does, that's where, as we've seen with the bridge, famous bridge collapse.
Oh, the Tacoma Narrows Bridge.
Yeah. So that got into in a resonance, and that was it.
And took it apart. Yeah. No, but the argument was that, there's a few peaks in every truck's drive or route that are dominant. And so if we can secure our products or protect it from those, the drive isn't long enough that just the road vibration or the engine vibration isn't sufficient to cause significant damage. So we're not going to worry about that. And the same with like solder joints is, we're going to model that, the maximum thermal cycling. Now there's all kinds of other things that can happen, but either the frequency of very large shocks on, say, a server circuit board is pretty insignificant in probability of occurring versus the everyday thermal cycling that eventually takes that solder joint apart. But there's back to the corrosion and cracking and those kinds of things. It is so dependent on the use cases and where it's located in the world.
Exactly.
If we put a device up in your neck of the woods in the 5,000 foot elevation, air's thinner, so you get a bigger daily temperature change than a lot of places do.
Right, and when the sun is 17% more energy than at sea level, up here there's 17% more energy in the sunlight, so things heat up quicker, and so and there's more differential across the structure in temperature because of the, capacity of the air, the sun, energy. And so, yeah, right. So, right. And the materials make a difference. Even one solder type, we've got now with lead free, we've got several different
Oh,
mixtures
yeah. I
of
saw a
solder.
list the other day. It was like 15 different formulations.
And I'm sure they don't all crack at the same rate.
No.
I mean, they don't,
No.
they fatigue differently. And certainly as we moved into lead free solder, we realized that, yeah, there's more of a brittle function. I mean, lead, we knew all about leaded solder.
Well, 50 plus years of playing with it.
Yeah, and it was very forgiving, kind of had a relaxation, So there are characteristics that change over time, and as we evolve in our materials science and materials, and of course the whole lead free was a legislative action. I don't know that we would have gone without the
no, the solder is more expensive.
Yeah, and we knew so much about lead solder. Some people would say that probably was a mistake for maybe the wrong reasons. I don't know. It's too late.
Well, it's pretty good not having lead in your water systems and stuff like that.
Right.
Look at the Romans. There was one of the theories is the way they all failed is they had lead pipes for their aquifers.
Yeah, we don't want another Flint, Michigan.
Well, there's that too. It's like we haven't learned in 2,000 years, but we try.
Right. But we're trying to not. Obviously, we don't want to throw. Part of that was electronics ending up in the landfills, which I think will always still be a
problem. Yeah. Now, one of the things that is curious is that I ran in recently to, and I use this as an example when I was answering this question about the crack propagation and analysis and so on. It was a different group, and they were talking about, well, we have this temperature humidity chamber, and so that's what we use to qualify our designs when they come through. And I says, okay, great. What failure mechanisms are you trying to find that you solved? What's your use environment? It's all on the coast. It's, we put this equipment on piers along the coast. And he says, do you add salt to your humidity? Oh no, it makes the chamber fall apart. And he says, right. Well, what kind of failures do you see in the field? Oh, we have salt corrosion all over our products all the time. It's like, kind of missed something there, didn't they? Yeah. Well, I think part of the disconnect is that, the testing equipment and so on is a big capital purchase for many organizations, right? Or if they're renting it. And you got to narrow it down. There's not a salt chamber with vibration, temperature controlled, and it has insect infestation all at once. We just don't make those that often.
Right. It was like putting, and there were companies that were putting. You had the traditional Halt chamber, which was vibration and rapid thermal liquid nitrogen cooling, and there were one or two companies that tried to put humidity in that situation,
and it would just destroy the hammers.
Yeah, it was just not a good idea. So,
well, part of that is that the equipment is accelerating. We're using higher temperatures or higher temperature transitions. We're doing, different kinds of vibration and higher vibration than would exist in the normal process. We haven't made high temperature bugs yet, and that will crawl through and eat your insulation of your product.
No,
they need nominal temperatures. But it's this
global warming will change that.
Yeah, we're working on it. But part of it is our experimental method and our ability to model multivariable factors and interactions and all that stuff. We even in complex models, we assume the variables are independent. Even though wink, wink, nudge, nudge, we know they're not.
Exactly. Sometimes I think we're delusional about, the complexities of it. As Einstein talked about, our prediction of the weather. And even with all our computer models and everything we have and all the measurements we can make and satellites and pressures and, just
don't forget
amazing.
atmospheric rivers that we've had out
here. And yet we're really not very good at predicting much beyond a week. 2 weeks.
Yeah, maybe 10 days.
I would trust any prediction 2 weeks in advance.
Well, what's amazing here is that I can look at like a weather website that has our local weather, and they'll show it by the minute when you expect the rain to start. And
Yeah,
like at 10:05, the rain actually does start. It's scary accurate.
Yeah,
but it's only a day.
Term,
it's only a couple hours ahead of that.
Only a couple hours. Yes, they've gotten very good at watching the clouds come in over your area.
Yeah.
But telling you that that's going to happen 2 weeks in advance, like your what do you call it, atmospheric river?
Yeah.
That caused a massive destruction in California that so desperately needed the moisture.
Yeah, but not all at once. We didn't need it all at once. We didn't need reservoirs overflowing, all kinds of stuff.
So, and we certainly, with hurricanes and tornadoes and everything, we really only know those things about the time. And it's just like knowing, something about a failure mechanism that's pretty clear, like a mismanufacturing where a package lead frame is off and misadjusted. Those kind of, it's the immediate things. Okay, and it's just like that with the weather. We can't really predict far in advance, but we can know, by looking at a problem or some issue on the board, a short-term failure.
Yep.
Is much more identifiable.
Well, part of it is that we want to simplify it so we can make some estimates, and we have this desire to go, will this last 10 years or not, kind of thing. And so we do a lot of different things, and which we've talked about in the past, to try to get a handle on that, try to get a reasonable or a rational or hallucinogenic, as I think you would say, estimate of its future performance.
Even though it will be technologically obsolete in 5 years, and
it won't matter anyway. But the idea is that some of it is the scientific method and our ability to reproduce results and do all these kinds of things, and then correlate them to and do all the statistics type stuff and everything else. And as soon as you get done with the 6-month study, somebody changes the solder paste, and now it's all different. Right.
Or that component, things that you model no longer exist. If you've been modeling leaded solders, that no longer exists. You got to go to lead-free model, and that's very different.
Well, at some point, and I think I find it with electronics, is that, the 0406 capacitors. I mean, you can see them. They're kind of nice.
Barely.
But then they get down to these, they're fractions of stuff. They're below a millimeter across kind of thing. They're just tiny little specks, or they're built into the circuit board. But the role of the way that material behaves to strains and stresses and reacts with solders and thermal cycling and everything else,
it's very complex,
very different. And then at some point, the size of them is such that the corrosive path across the body of it is so short that dominates rather than solder joint failures or cracking of some sort. And so we get this problem.
And half the locations of those don't really matter if they fail or not.
Well, there's that too, capacitors in particular. I remember working with an electrical engineer once, and I said, why are there so many capacitors on this? And he goes, well, I don't have time to sort out which ones I really need, so I just put them all on
exactly. there. Just kind of a safety margin. Just put them all over the place to
knock down it was the electromagnetic problems, transients, knock down spikes, all kinds of reasons.
They're hard to add afterwards. It's easier to add them and, maybe
take them off later. Yeah,
exactly.
And he said it's sort of like I create the basic functional design, and then I take out my salt and pepper shaker of different size capacitors and sprinkle them all over the board. And he goes, yeah, that's about how I design it.
Yeah. It works for me. And they're not that expensive, so it's not like a major IC. You just, they're fractions of a penny.
Well, there are, but when you put 200 of them on the board, one, the board's got to be bigger, and two is you got to place them all, put solder on it. And then at the time, I found from one of the big failure analysis labs that 1/3 of the problems from circuit boards was due to capacitors.
Yeah.
And I said, so the guy I was working with said, well, that gives us justification to do a cost reduction program next year, so we can now take off capacitors and get paid to do it in a rational way so that we save money on, one, the components, but two, reducing failure rates. Okay, I get it.
Oh, man. It's just like security. When I told some of the engineers in Dell, I said, look, these boards will operate at 135 C if I suppress the CPU's thermal trip.
Yep.
And he said, well, is there some way we can get them to operate at, limit or get some money? Essentially, we don't need that. So why can we somehow make, them operate at 100 degrees C and our
Maybe
max?
you can put them in different places,
Or no, or not that, but they wanted to take out the money. That was too much margin.
Yeah.
Can we exchange margin for some savings?
Oh, sure. We'll get rid of the silicon and we'll use
Yeah.
silly putty instead.
Yeah, exactly. I'm thinking, no, my point is use the strength you have that's inherent in the product to find the outliers, the ones that are
worth solving. Get rid of the fans.
Exactly, the ones that have latent defects. Use that strength. You're just wasting it. When you put it, when you do a 45-degree, burn in, then that's just a waste of time.
Yeah,
of course, it's going to operate that. And they had this huge room where it was, 40 degrees C, I think, 90, 97.
And it was self-heated from all the servers that were running.
Exactly. And they had them cycling. Anyway, I won't rag on them.
Well, we've talked about a handful of these before, but the ones that get me is they're solely focused on the CPU and they're running all these tests and all this stuff, but the memory chips that are part of the board that are supporting that circuit are failing in the testing that they're doing for the CPUs. And I says, well, why aren't you addressing the memory failures? Well, we're studying the CPU. We're not studying the memory. That
was another problem. Those the little DIMM boards you used to plug in and out of your PC, the edge connectors would come from the suppliers with not really clean contacts.
Not clean, and also not really useful for putting in and out very many times.
Right, exactly. They're right.
Cycles.
It was gold, so they would try to save on the gold molecules, and they would have one layer maybe, and if you plugged it in more than once, you'd scrape that entire layer off, and you'd get fretting corrosion. Yep. But I would always deal with the fact that I got the new ones, and they weren't clean, and we put them in an 85, that's 85 degrees C at 85% relative humidity. And
they probably corroded right up, didn't they?
Eventually, yeah. And I would get memory issues. And, according to protocol, test protocols, I was supposed to mark this down as a failure. But it happened so many times, I kind of refused to do the test because it would always go into the same ridiculous cycle. Tell the vendor they need to clean them better, something like that. And, maybe they would for a while, but eventually they didn't. Yeah. And it was just kind of a churn of something that was a known process variation that caused a problem. But it was also very difficult to isolate because as soon as you plugged in and out that DIMM, problem was corrected. Problem disappeared.
For a while.
Right. You'd have to go through put it in a high temperature. Corrode again. Trying to troubleshoot that, you wouldn't, unless you had a factory that's building a lot of these, you wouldn't know that. And some people at the company levels that maintained them would plug them in and out, and that's sometimes, as I say to,
we get fresh metal on it. You're all good.
And it's like we say with a computer, the first thing to do is reboot it and reset it.
Well, it used to be that you hit the side of it because it'd reset all those cards.
Yeah. Right.
But the idea, though, is that many of the failure mechanisms we deal with don't have a single stress. Now, some will have a dominant stress.
Most failure mechanisms have interactions with stresses.
And so it really behooves people to think through what's the environment, what's typical stresses you're getting on this thing, and understand those failure mechanisms, and don't ignore the second order effects, because in your circumstance, that may be dominant. Like the salt on the coast.
Right.
They didn't want it. We only use distilled water in our chambers. That's not terribly useful.
Well, that's another corrosion, believe it or not.
Yeah. No, there's all kinds of weird stuff.
People don't realize
water is too clean.
Pure water is corrosive.
It's known as the universal solvent for a reason. It takes everything apart. But anyway, the idea of thinking through what are you studying, trying to model, what kind of test you're running, what kind of analysis you're doing.
Right.
Most of that kind of work is just an estimate. And so stepping back and thinking through, am I working on the right estimates, the ones that matter, the ones we can
Right.
do anything about?
And at some point, they have to be validated. You have to show that that's either from field data or field or own testing.
Yeah.
You just
Well,
can't-
that brings up a whole other topic. How do you go about proving this stuff?
Yeah.
But that's another topic.
Right.
But anyway, it was an interesting question, back and forth. I talked about it on another episode more directly of what the degradation data or estimate or a data analysis was, or maybe I haven't yet. I'm not sure. It's in my list to talk about.
Okay.
But I knew that I wouldn't want to bore you, Kirk, with talking about data analysis for degradation of a crack propagation.
Well,
some
that- yeah.
critical modeling techniques there.
Right. I'll believe any of that if you show me that you validated it with real data.
Oh, we
and
don't have time for that.
experiment.
It takes years.
Just believe me.
Yeah, just believe me. I ran it out to 16 digits. It must be true.
Exactly.
Yeah. But anyway, if you got a question or interesting failure mechanism or modeling or whatever you're working on, let us know. Head over to accendoreliability.com/go/SOR, and you can find a couple of different ways to get in touch with us. Kirk and I and the other hosts are available through LinkedIn or through our About pages, where many of us have contact and or just our email directly there. And given the last week, apparently the words got out, or it's just gotten through the holidays, and people in February, when we're recording this, have figured out they got questions. And so we've been getting a few of them. So we appreciate that. And Kirk, I'll have to take a look at the stack we got and see what we could talk about next.
Yeah, we love those questions. So keep sending it in, and thanks for listening, everybody.
All right. Thanks, Kirk. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.